Okay, there was a question about integrated assignment 3, question 4, which kind of says find V, the potential, at the point P. And I just kind of drew the setup here. I added, what we're going to do is add up all these DQs, right? Here's this uniform charge distribution. There's a Q here, DQs going all the way. And we're going to add them all up. And we know each of these DQs adds a little bit of potential dV, right? And we can kind of use that point charge potential formula. dQ equals K, dV equals K dQ over R. Notice a few things. This is R, not R squared, right? Because we're talking about potential, and there's no R hat. And so what you kind of need to do is figure out those three things. You need to figure out what R is. You need to figure out your limits of integration. And you need to figure out dQ. Right? Those are the three things. And what I would do is kind of look at, we did this same problem with electric fields. This geometry is the same. So your R will be very similar. Your limits of integration are probably going to be similar. You can define x equals 0 wherever you want. And dq might be pretty similar. It's probably also going to be related to a constant here. And so you'll plug these three things into here, maybe following those same steps that you did in integrated assignment 2, but into a different formula, and end up with a slightly different integral here. So you'd end up with some V is integral K dQ over R. But then there's the matter of changing Q to maybe something in terms of dx, or sorry, dq in terms of dx, and then your limits will be x equals something to x equals that final point. But I think I would mostly look at integrated assignment 2 problem 1 to fill these parts in. Cool.